Greetings and welcome to the McGregor Magic Festival. I'm sitting here in George on the garden route, preparing some information about Mother Earth and the science of her larder. And it's based on 53 years of experience, which I have in organic agriculture, 20 years as a farmer, 20 years training organic farmers, and then 10 years as a professor of soil science and plant production at Nelson Mandela University. And more recently, I've been put onto the board of the South African Organic Sector Organization and the Agricultural Research Council. So I'm more and more involved with policy work and also helping the African Union to assess how we can mainstream what they call ecological organic agriculture throughout Africa. So these are exciting times, and it's great to be able to share with people who love the soil and who love gardening some of the basic ideas about how organic farming can be a useful approach to producing food. I'm going to share the screen and use a PowerPoint presentation to give the outline of what I'm hoping to do, as well as the first of the basic soil fertility talks. So bear with me while I see if I can open it up. And unfortunately, the technology doesn't allow me to make a full screen. So I'm just going to make a reasonably large screen and make sure that that works rather than trying to go for everything and get nothing. So the science of Mother Earth and her larder. This is a background presentation, and in fact the PowerPoint presentation with all 5 sets of background for the 5 videos will be on the McGregor Magic Festival site. The topics are first the basics of soil fertility, which is the subject of this video, and then we'll move on in the next video to compost and the soil's capacity to hold water and nutrients. Then we'll look at designing and setting up a crop rotation, and having done those 3 topics, we should be able to understand why soil acidity is important and how to sweeten acid soils. And then we'll go on to a brief discussion of pest and disease management at a very basic level. And then we'll have a little PS, which is about how the organic sector is organized in South Africa, Southern Africa, and globally. So if we want to understand the questions around soil fertility and also the problems of climate change, we have to look quite carefully at how carbon functions in the global carbon cycle. Around the world, we have a huge amount of carbon. Some of it is in the form of carbon dioxide or carbon monoxide, a gas which, as you know, is too much of it in the air and causing global warming. It's making kind of a blanket, and the heat can't get out as much as it used to. So it is conserving energy, but in fact, too efficiently. And this means that the carbon is stuck in the atmosphere, and it should be in the soil. Carbon in the soil in the form of colloidal humus is a really, really good holder of nutrients and water, but carbon in the atmosphere creates a greenhouse. Now I'm going to be talking about petagrams as the units of carbon, and a petagram is an enormous unit. 1 billion tons of carbon is 1 petagram. So when you look at the total amount of carbon produced every year by factories and motor cars and put into the atmosphere, it's about 7.5 billion tons that goes into the atmosphere every year. And unfortunately, the atmosphere is getting more and more carbon, so much so that 105 petagrams falls out into the sea every year, but about 102 petagrams evaporates in the form of carbon dioxide from the sea. So each year, about 3 petagrams of carbon fall into the sea in terms of the net balance, and that means that more and more carbon, as well as other nutrients, are helping to acidify the soil, the sea, and together with plastic pollution, you'll be aware that the sea is in a lot of trouble, and we're in a lot of trouble because we are not respecting the sea. So this is the right-hand side of this picture, which has to do with pollution, atmospheric levels of carbon going up and up, and the amount of carbon in the sea going up. On the left-hand side, we have the agricultural part of the equation. We would like to have as much as possible carbon in the soil, and also the more we have in the vegetation, the better. But as you can see, the vegetation is less than a quarter of the carbon in the soil, and all of the forests and all of the crops in the world are recycled into the soil, and the amount of carbon that goes into the soil each year is about 60 petagrams, 60 billion tons. That would be fine if 60 billion tons was also going out of the soil, and then we would have a proper cycling process. But in fact, 62.5 billion tons of carbon leave the soil every year, and only 60 billion go in. So every year we're losing 2.5 billion tons of carbon, mostly into the atmosphere. And about 2/3 of that is in the form of burning of forests, where the carbon dioxide from the forest goes into the atmosphere. And about 1/3 of it is because of the plowing of soil. If you plow your soil, especially with a rotavator or moldboard plow, as you turn over the soil, the subsoil is exposed to the air, and the carbon dioxide, the carbon is oxidized into carbon dioxide and goes into the atmosphere. So this is a very bad situation. Between deforestation and bad plowing, we are causing carbon dioxide to leave the soil, go into the atmosphere, and this is depleting carbon stocks in the soil and adding to global warming. So instead of agriculture being part of the solution to climate change, at the moment, agriculture is adding to climate change. Not only is there the carbon from the soil, but there also are methane gas, CH4, from cattle and from other sources of pollution like landfill sites. So we've got the methane, we've got the carbon dioxide, the carbon monoxide from vehicles, and CFCs from refrigeration, all adding to the atmospheric pollution and the global warming. If we could turn this around, if we could first balance the carbon that goes in and the carbon that goes out, and perhaps eventually, at least for the next 10 or 20 years, make more carbon go into the soil than goes out. So we might have 62 petagrams going in each year and only perhaps 58 or even 56 going out, while we are building up soil carbon reserves in the world as the world changes to agroecology and organic agriculture. This would make a huge difference to helping reduce the atmospheric carbon pollution. But as I say, we can only do this for 10 or 20 years until we have built up carbon stocks in the soil. So at the same time as we're converting agriculture to agroecology, we have to clean up the industries and the mobility side of things. We have to have more efficient aeroplanes, more efficient trains, and above all, more efficient vehicles using renewable energy rather than burning fossil fuels. If we do that, then we will be able to change around this global warming situation, and we have to do it for the sake of our children. So it's part of understanding why Mother Earth is in so much trouble, and it's part of the reason why organic agriculture and agroecology and conservation agriculture are such an important part of changing things around with the environment. If we look at the change over the years, I've been 53 years involved in organic agriculture. And when we started, it was chemical monoculture. There was also some organic farming and there was some biodynamic farming. But what we've seen over the last 50 years is gradually the growth of alternative conventional agriculture. First, the farmers began to realize that they should integrate the arable farming with some livestock farming. Then they needed to cut down on the amount of poison they were using, because the consumers were saying, we're not going to buy your crops if they are so full of poison and if you destroy the environment. So conservation agriculture evolved, and conservation agriculture is now quite well known, and our government Department of Agriculture is supporting it. And CA, conservation agriculture, has three principles. The first is that they use as little tillage as possible. I explained the bad effects of tillage, how it allows carbon dioxide to be oxidized and the soil carbon turns into a gas and is lost to the soil. So they use minimum tillage or zero tillage. The second thing they do is they use mulches to cover the soil. And the third thing is they introduce crop rotation. So conservation agriculture is already halfway to organic farming, and biological farming is 2/3 of the way towards organic farming, because the biological farmers understand the soil biology, they understand how to use compost and soil organic matter, and although they may still be using some fertilizer and poison, they're well on the way to organic farming. So we are wonderfully happy that many farmers are beginning to understand the soil biology and going in the right direction. Beyond organic farming, you have permaculture, which is a planning design methodology that helps you to understand the flows of energy and the flows of wind and water on the farm and to design around them. You have the French intensive method, which uses double digging. And then right at the end of the spectrum, perhaps you have biodynamic agriculture, which is a very esoteric approach to developing a farm organism that is balanced in terms of the human activities, the animal activities, the perennial plants, the annual plants, and the minerals and soil. So biodynamic agriculture in many ways is the ultimate form of sustainable agriculture, but it does upset a lot of scientists because it is quite a deeply spiritual approach to agriculture, and a lot of the processes that are involved in biodynamics are very difficult to explain to materialistic scientists. The basis of soil science, as soil scientists see it, is that soil science stands on 3 legs: soil physics, soil chemistry, and soil biology. The physical leg is what I will explain first, which is very easy to understand. The chemical leg is quite complicated and takes a little bit of basic chemistry. The biological leg is more intuitive, and the biological leg is really the core of organic agriculture. So let's first look at the physics. The physical structure of the soil depends on aerobic conditions. In the little picture that you can see on the screen, on the right-hand side, you can see what is essentially concrete. The soil is compacted, the little roots cannot move, there's no air in the soil, and the water will not readily go into the soil because of the lack of macropores. On the left, under the magnifying glass, you can see the crumb structure of soil, and it has macropores. It has these big gaps in between the particles of soil. And in these gaps, you find plant roots, you'll find earthworms, you'll find water, and above all, you'll find air, oxygen and nitrogen in the soil. Very, very important. Why? Because if you don't have air in the soil, you will find the soil biology and the soil chemistry don't collaborate very well with the farmer. What causes the air to be squashed out of these macropores is mainly bad cultivation. Moldboard plows and rotavators and also heavy vehicles cause soil compaction. They literally squeeze the air out of the soil. Careful tillage with the chisel plow or with the garden fork leaves the soil structure intact and promotes aerobic conditions in the soil, and it's a way of breaking up plow pans caused by bad plowing or compaction from heavy vehicles, or even walking. If you walk up and down a path, that path creates a plow pan underneath where the soil has been compacted by human feet thumping up and down or cattle thumping up and down. So we really need to think of the soil as a delicate living organism, and it's vitally important that we have aerobic conditions under the surface of the soil. Rotational grazing allows the roots to grow undisturbed while the field is rested, and if you have different types of plants, the different types of roots, deep roots like lucerne or alfalfa, shallower networks of roots, and a whole range of tap roots and networking roots are really important as part of your rotation planning, which we'll discuss later. Really important also is soil organic matter, which helps the soil structure, which is very much a part of organic farming. Moving on then to soil chemistry, the essence of soil chemistry is that acid soil locks up nutrients. If your soil is acidic, if the pH is well below 7, then the phosphate may not be available to plants. The pH scale goes from 0 to 14. It's a logarithmic scale. So a pH of 7 is neutral. A pH of 6 is fairly acid. A pH of 5 is 10 times as acid as a pH of 6. And a pH of 4 is 100 times as acid as a pH of 6. So the concentration of the hydrogen ions in the soil is called pH, the power of hydrogen. And that pH scale is well known to most people. pH below 7 is acid, pH above 7 is alkaline. We occasionally do get alkaline soils, but most of the soils in South Africa are pretty acidic, very often with a pH around 4, which is very difficult to grow crops on. Once your soil gets between 5 and 6, although it's still acidic, most crops will grow and most nutrients will be reasonably well available. But below 5, you'll often have exchangeable aluminium or exchangeable iron oxides. And these iron oxides and aluminium oxides will very often tie up the phosphorus that is present in the soil, and then it will not be available to the plant roots. If you add lots of good compost, the compost will add carbon, and this will buffer the soil acidity. And you can gradually sweeten up your soil with compost and crop rotation. Many farmers choose to do it quickly with lime, and they may need to add a few tons per hectare of lime. I never add more than 3 tons per hectare at a time, and it'll take a few months. You need to incorporate the lime, but lime is ground up rock dust, and it will neutralize soil acidity, and the toxic aluminium will be kept out of circulation so that the phosphorus will come into circulation, become more available. If the magnesium is in short supply as well as acidity, then you would use a dolomitic lime, otherwise a calcitic lime will be acceptable. So the soil chemistry is a very important part of what needs to happen, but it is very much related to the soil biology, and we need to understand that soil biology is very much a part of how we have to integrate the physics, the chemistry, and the biology in order to make conditions acceptable to the small organisms in the soil. But we need the N, the nitrogen, the P, the phosphorus, and the K, potassium. The N and K are usually available in compost, but P, the phosphate, is not. So many organic farmers who are anti-using any fertilizers will find that they're not getting good yields of crops because their crops are starved of phosphorus. You can put phosphorus as rock phosphate, commonly available Langphos, which comes from the Western Cape, from Langebaan. These are ocean deposits, which formerly the whole of the West Coast was covered by sea, and these were little shellfish with a lot of calcium and some phosphorus as well, and it makes an excellent organic fertilizer. You only need to use it once, but you might need to have quite a generous dressing to bring your soil phosphorus up to a level where it will then remain available at high enough levels to not restrict crop production. Soil analysis will tell you what your pH is, whether your soil is acid or alkaline. It will tell you the levels of carbon. It will tell you your phosphorus levels and whether the phosphorus is available, and the same with the potassium. Soil biology is rather different. The main thing that we understand in organic farming is that red wriggler worms are compost worms. We see them in the compost. The fishermen love them. They live in the litter layer of the soil, and they digest dead organic matter very, very quickly. The larger gray earthworms live a little bit deeper in the soil, and they work more slowly, but they're equally beneficial, but they just work a little bit more slowly. And you also have vertical anisic earthworms, which burrow up and down. But all of these earthworms eat organic material, and their burrows are lined with colloidal humus, which is just like compost and which is pure plant food. So these earthworms are very, very important to organic farmers. If we have a look at the even smaller organisms, we can see earthworms with our eyes, but fungi we can only just see with our eyes, and bacteria we can't see at all unless we have a good microscope. So illustrated in this slide are mycorrhizae, which means really root fungi. They're beneficial fungi. They live in symbiosis with the plant roots. they enlarge the surface area of the roots and penetrate the very tiny small pores, and they help the plants in taking up nutrients and water. And there's a symbiotic exchange that the mycorrhizae get from the plant some of the sugars and provide to the plant some of the nutrients that are extracted from the soil. They improve the soil structure and they preserve moisture, so they're very important, but they are very, very sensitive to chemical fertilizers and pesticides. So as soon as you start using poisons or chemical fertilizers, you will find you have no fungi, and again, you will lose these very valuable helpers that the organic farmer desperately needs. Now, apart from the aerobic conditions in the soil, a really important part of organic agriculture and soil management is, as far as possible, to cover the soil with mulch. I mentioned that conservation agriculture uses the three principles of minimum tillage, crop rotation, and mulch. And all organic farmers try to use mulch wherever they possibly can, where they can find enough organic matter. They spread it as a blanket on top of the soil. It keeps the moisture in the soil, reduces evaporation. It also smothers a lot of the weeds, and it is basically slowly going to convert to soil organic matter as the decomposition happens under the mulch layer. This can give rise to a nitrogen negative period, so you have to be sure that if you're putting a lot of mulch on the top of the soil, you feed the crops with enough compost that they will not, in the short term, find themselves short of nitrogen. Now, an important thing to understand in terms of soil biology is what we call the bacteria and fungi, which are aerobic, as against the bacteria and fungi, which are anaerobic, which cannot survive in the presence of oxygen. And we have a third group, the facultative anaerobes, which can survive either with oxygen or without oxygen. But because these facultative anaerobes, which are the bad guys, these are the disease organisms, the pathogens, which are very much involved in spreading diseases in the soil, such as rhizoctonia and many other rusts and bacterial and fungal diseases. These facultative anaerobes are really sophisticated in that they produce two sets of enzymes. One set of enzymes helps them deal with respiration with oxygen, and the other allows them to survive in the absence of oxygen. But because they produce two sets of enzymes, they're not as efficient as the aerobic bacteria, which only produce aerobic enzymes and are specialized to only survive in aerobic conditions, which means they're more efficient than the facultative anaerobes when conditions are aerobic. That's why it's so important to keep conditions aerobic. As soon as they go anaerobic, the facultative anaerobes, which have been surviving under aerobic conditions, all of a sudden start to thrive because they don't have competition from aerobic bacteria and fungi. And so we find as soon as our soils go anaerobic or smelly or very often waterlogged, the bacteria and fungi that are facultative anaerobes, the pathogens, disease organisms, they take over, and we find the soil becomes very unfriendly to plant growth. So the final topic I want to deal with in this little video is soil organic matter, which is made up mainly of carbon. And when it decomposes, it becomes active biomass or effectively compost. So we may make the compost in a compost heap, or we may have our earthworms eating dead roots and turning them into colloidal humus. What comes out of the back end of an earthworm is some of the best compost that you could hope for. So whether it's a red wriggler in your compost, or whether it's the gray earthworm or the red wriggler in the soil, the excretion of these worms is really what we call colloidal humus, which is the most useful substance that we can possibly have in our soil. Because it's a colloid, this humus can hold water and nutrients, especially positively charged cations like calcium, magnesium, and potassium, and it thus increases the cation exchange capacity of the soil. CEC we'll find in the soil analysis. The plants are able to take up these cations because of the negative charges on the surface area of the compost or of clay colloids. And that means that the plant can come along with its little roots and almost pluck off those cations, which it then uses to grow healthy. So that's all I'm going to say in this particular video, and we'll come back to the rest of the topics in the next video.